Welcome to the Somnus Archive. You have entered a space of quiet observation and deep technical record. Before we begin today's log, I invite you to adjust your surroundings. Lower your lighting, settle into a position of absolute comfort, and allow the weight of the day to dissipate. In the archive, we do not rush. We prioritize the intricate, the methodical, and the still. Whether you are here to learn or here to rest, the information will remain. Prologue, the atmosphere as a slow ocean. We are not looking at the weather for the sake of the forecast. We are looking at the weather for the sake of its structure. We are going to categorize the sky, slowly, carefully, and with more detail than anyone strictly needs. The atmosphere is a fluid, a very thin ocean of gas resting on the surface of the Earth. It is composed primarily of nitrogen, oxygen, and argon, with traces of carbon dioxide and other gases, all held to the planet by gravity. Within this fluid, water vapor moves continuously, changing its state as temperature and pressure shift. When the temperature falls to what is known as the dew point, invisible water vapor begins to cling to microscopic particles that are already present in the air. These particles might be fragments of dust, sea salt crystals carried from the ocean, or soot from distant fur. Yes. They are called cloud condensation nuclei, the tiny, unseen anchors around which clouds are buoyed. Imagine a single droplet of cloud water. Its diameter is around 10 micrometers, which is 1/100th of a millimeter, much too small for the unaided human eye to rest. To form a single raindrop, perhaps 1 million of these tiny droplets must collide and merge together. But tonight, we are not concerned with the rain that eventually falls. We are interested in the suspension, stillness, the taxonomy of vapor. As we proceed through this extended log, we will move gradually through the different levels of the troposphere, the lowest layer of the atmosphere, and we will revisit each primary genus of cloud with addition. I'll detail. Between each section, we will pause to consider the instruments and definitions that allow us to measure and name what we are observing. If you notice your attention drifting, that is acceptable. In the archive, distraction is simply another atmospheric condition, observed with judgment. Chapter 1. The high Étage, above 20,000 feet. Before the year 1802, clouds were often regarded as too chaotic to classify. They changed shape rapidly. They drifted. They dissolved. They reformed again somewhere else. And to many observers, this motion seemed too restless, too inconsistent, to be placed into a neat system. They appeared to resist systematic description. Every time you looked up, they were slightly different. Every time you tried to fix them in words, they had already become something else. To many, they were beyond the reach of science. They belonged to poetry, to superstition, to casual conversation about the weather, but not to careful measurement or taxonomy. Pause for a moment here. Picture a sky before names, before categories, before diagrams and charts. Just vague shapes, without labels, passing slowly over the land. A Quaker pharmacist named Luke Howard did not agree. He treated the sky as a laboratory. He treated clouds not as random decorations, but as recurring forms, repeating patterns that could be observed, compared, and eventually named. He stood beneath the same changeable sky, but instead of seeing chaos, he saw families of shape and structure. He saw that some clouds were heaps, some were layers, some were wisps and threads. Using Latin, influenced by the Linnean system of biological classification, he introduced a structured vocabulary for clouds: cirrus, cumulus, stratus, and their combinations. These names may sound abstract, but each one is simply a careful label for something you have already seen many times, without necessarily naming it. If you wish, you may imagine Luke Howard standing in a quiet field, looking up, noting the forms of the sky, and slowly writing them into a notebook. The clouds move, but the names remain. We begin our documentation at the highest reaches of the troposphere. The troposphere is the lowest major layer of the atmosphere, the region where almost all weather occurs. We are now interested in its uppermost part, above roughly 20,000 feet, where conditions are cold, dry, and thin. Here the air is thin, and the temperature is permanently below freezing. There is less oxygen, less water vapor, less of everything, except for motion and cold. At these altitudes, clouds are not composed of liquid water droplets, but of ice crystals. Each crystal is very small, with an average diameter of roughly 25 micrometers, a size too fine for the human eye to resolve individually. When you see a pale streak or veil of high cloud, you are looking at vast numbers of these tiny crystals, drifting together, moving as one large slow structure across the sky. Take a quiet breath. As you exhale, picture that high cold layer, sharp blue above, delicate ice below, far away from the surface where you rest. 2. The genus Cirrocumulus. We now observe a shift in the physics of the high Étage, where cirrus clouds are primarily linear and fibrous. Cirrocumulus introduces a more granular, rippling texture. Instead of threads, we see small dots, small grains, small wavelets in the high sky. Cirrocumulus stratiformis, CC Street. Cirrocumulus stratiformis appears as sheets of very small white grains or rip. Please. The pattern can resemble fish scales, giving rise to the phrase mackerel sky. From a distance, the sky looks lightly patterned, as if a fine comb had been drawn gently across it. Each individual element is tiny, with no significant shading, indicating that the layer remains thin and composed rely of ice. The technical distinction between cirrus fibratus and cirrocumulus stratiformis lies in the underlying dynamics. Cirrus fibratus is shaped primarily by horizontal winds stretching existing ice crystals into elongated filaments. Cirrocumulus, by contrast, arises from vertical instability. Small pockets of air rise and sink again, creating a pattern of gentle afts and downdrafts. This motion arranges the cloud layer into dappled patches, bright where the ice is slightly thicker, slightly less bright where it is thinner, though at these heights, the contrast remains subtle and soft. If you see a mackerel sky above you, you are looking at evidence of these small vertical motions into the otherwise quiet high air. Cirrocumulus lenticularis, CC Len. Cirrocumulus lenticularis forms as smooth, lens-shaped patches. These clouds often appear over mountain ranges, aligned with atmospheric waves that are generated when stable air flows over topographical obstacles. The air is forced upward on the windward side, then downward on the leeward side, eating standing waves in the sky. Where the air rises and cools, clouds form. Where the air inks and warms again, they evaporate. Although these lens-shaped clouds appear stationary, air continuously flows through them, condensing on the upwind side, evaporating on the downwind side. The cloud remains in place, but the particles that decompose it are constantly being replaced. When the temperature remains consistently below -30 degrees Celsius, these lenses persist as thin, layered structures of ice. They may appear stacked, one above another, like a pile of smoot, each pale stones, hovering quiet, ly in the upper air. 3. The genus Cirrostratus. We now move to the veil of the high Étage. Cirrostratus is less about patterns and more about coverage, less about individ UL shapes, and more about an sky, gently filled. Cirrostratus nebulosus CS neb. Cirrostratus nebulosus appears as a thin, whitish, featureless sheet, covering large portions of the sky. It does not usually draw attention to itself. It has very little texture. It can be so subtle that you only notice it indirectly. It is often only noticed when it produces a halo around the sun or the moon. This halo has a radius of approximately 22 degrees, set by the geometry of light, refracting through hexagonal ice crystals. Light enters a crystal face, bends, and leaves through an off or face, producing a fixed angle of deviation that we see as a ring. A cirrostratus layer can extend for hundreds of kilometers, indicating broad-scale lifting of moist air in the upper troposphere. From ground level, this simply appears as a gentle whitening of the sky, a softening of sunlight or moonlight, a sense that a thin, high veil has been drawn across your field of view. Interlude. First instruments, the barometer. Before we descend to the middle Étage, we pause to consider one of the archive's fundamental instruments, the barometer. It measures the weight of the atmosphere itself. Even now, as you rest, the entire column of air above you is pressing down. You do not feel this pressure directly because your body is adapted to it, balanced with it, but it is always there. The classic Torselian barometer consists of a glass tube, sealed at one end, filled completely with mercury, and then inverted to a reservoir. When the tube is inverted, some of the mercury flows out, but not all of it. At the top of the tube, a space opens where no air is present. This is the Torselian vacuum. The atmosphere's weight on the reservoir was heaves mercury up the tube. The higher the external pressure, the higher the column of mercury climbs. On a calm day at sea level, the height of the mercury column stabilizes around 760 millimeters. When the air grows heavier and cold, the column rises slightly. When a storm approaches and the air becomes less dense, the mercury level falls. A simple glass tube and a pool of liquid metal thus become a record of the invisible weight of the air above. In the 19th century, the aneroid barometer was introduced. Contains a small, evacuated metal capsule that flex in response to changing air pressure. As the pressure outside increases, the capsule compresses slightly. As the pressure decreases, the capsule expands. This tiny movement is magnified by levers and springs, turning a needle over a dial, often marked W. Words such as fair, change, and stormy. The needle moves slow, almost imperceptibly, as the atmosphere shifts. In the archive, we record not the words on the dial, but the numbers and the slow, patient movement of the needle over time, hour after hour, day after day. The instrument marks the rise and fall of the air's weight, a quiet, mechanical heartbeat of the sky.
Chapter 2. The Middle Étage, 6,500 to 20,000 feet. As we descend from the high Étage, we enter the mid-level region of the troposphere. We are no longer in the realm of pure, delicate ice, and we are not yet in the dense, heavy air near the surface. We are moving through a middle world between the high, cold filaments and the low, dark lay airs. The air here is denser than in the high Étage, and clouds increasingly contain liquid water droplets. In addition to ice, some droplets are still frozen, some are liquid, some are in between, waiting for the right particle, the right moment to change their state. The Latin prefix used for this level is alto, meaning high, though in our vertical classification, it indicates T, middle range. So when you hear alto cumulus or alto stratus, you may think cumulus of the middle level, stratus of the middle level, clouds halfway between the surface where you rest and the cold ceiling of T, troposphere above. Pause for a moment here. Imagine yourself between two ceilings, one made of thin ice filaments above, one made of heavy, darker clouds below. The middle Étage is the softly lit hallway between those two floors. The genus Altocumulus. Altocumulus is the most diverse. The middle Étage genera. It often signals a sky in transition, where the atmosphere is neither fully stable nor fully disturbed. Atmospheric waves and convection create patterns of light and shadow, rows and patches, structures that seem to drift slowly, even as the air inside them moves in quiet, continuous motion. When altocumulus is present, the sky is telling us that layers of air are sliding over each other, rising in some places, sinking in others, trading heat and moisture in a patient exchange. Altocumulus flocus, AC flow. Altocumulus flocus appears as small, tufted heaps with ragged bases. They resemble small shreds of ton, or pieces of fleece, gently torn apart from below. Each tuft looks like a soft, rounded puff, with a frayed underside, as though someone has led very gently on the bottom edge of the cloud. These tufts are often accompanied by virga, thin trails of precipitation, evaporating before reaching the ground. You may see faint streaks hanging below each puff, like threads of fabric that never quite touch the earth. Each fragment of altocumulus flocus is an isolated pocket of rising air, capped and partially eroded by drier air around it. Warm, humid air lifts, cools, and forms a tuft. Dry air above and beside it nibbles away at its edges, shred in the base, carving the cloud into its characteristic frayed form. If you imagine each tuft as a breath, you might think of the sky inhaling in one place exhaling in another, creating a catted field of soft, fleecy ichthya, plations, suspended in the middle air. Altocumulus stratiformis, AC Street. Altocumu. Loose stratiformis forms extensive horizontal sheets of rounded elements, unlike the very high cirrocumulus.
TH.
Individual elements in altocumulus stratiformis show noticeable shading. Their tops are brighter, their bases slightly darker, indicating greater thickness, and a mixture of water droplets with ice crystals. The pattern may appear as rows, or as broader patches, with brighter tops illuminated by the sun, and darker undersides revealing more opacity. From the ground, you may see a field of soft, rounded shapes, each with a gentle contrast. Light above, shadow below. This shading tells us that these clouds are not delicate veils, but or substantial structures holding enough water to interfere with light in a visible way. If you lie back and look up at such a sky, you might notice that the rows and patches seem to drift slowly, yet their pattern remains recognizable. The middle edge is rearranging itself, but it does so in an unhurried, orderly fashion. Altocumulus volutus, AC vol. Altocumulus volutus is relatival. Why rare? It appears as an elongated, tube-shaped cloud that seems to roll along a horizontal axis. From a distance, it can look like a long cylinder of vapor, a cloud that has gathered itself into a single, continuous roll. This structure is usually associated with wind shear, where layers of air move at different speeds or in slightly different directions, rolling the cloud into a horizontal vortex. The Archive V notes these forms as visual evidence of shear and small-scale rotational motion. In the middle atmosphere, you may imagine this as the sky quietly twisting, not in a violent spiral, but in a smooth, slow rotation, turning a flat layer F cloud into a rolled band like a scroll of vapor, unfurling across the mid-level sky. Altocumulus opa, cos AC opa. Altocumulus opacus forms an opaque layer, where individual elements have merged into a continuous sheet. It is thick enough to fully obscure the sun. Under an altocumulus opacus sky, the light becomes diffusa and de-uniform, with few shadows. Edges soften, colors mute, and the landscape appears quietly flattened by evenly spread light. There is still structure in the cloud above, slight undulations and variations, but the ground. It presents as a single, dominant ceiling, sitting in the middle edge, between you and the high cirrus realm above. In such conditions, the sky feels low, even though the cloud remains miles overhead. The mind responds to the uniform ceiling, as if a roof has been gently lowered. Over the day.
2. The genus Altostratus. Altostratus appears, not in broken patches, but as a continuous sheet, where altocumulus provides texture, deeps rose waves. Altostratus smooths the sky into a more uniform lay. It is less about shapes and more about coverage, less about individual features and more about a broad, even press. Altostratus translucidus, strop. Altostratus translucidus covers the sky with a gray or bluish layer. The sun or moon may still be visible, but only as a poorly defined bright disk, blurred behind the cloud. You can tell where the light source is, but you cannot see its be clearly. Unlike cirrostratus, altostratus does not usually produce optical halos because the light is scattered by liquid droplets, not refracted by well-formed ice crystals. The droplets bend and diffuse the light in many directions, rather than bending it along precise halo-forming paths. The result is a sky that feels muted and subdued, quietly luminous without sharp beams or bright points. It is as if the entire dome above has become a single soft light source, spread evenly from horizon to horizon. Altostratus radiatus as rad. Altostratus radiatus appears in parallel bands, which seem to converge at a point on the horizon. Due to perspective, these bands are the manifestation of large-scale atmospheric waves, a slow undulation of the mid-level cloud layer. Imagine the entire layer of altostratus rising and falling in giant, gentle waves, too large to feel directly but visible in the alternating light and shadow of its bands. From your position on the surface, the lines of cloud seem to narrow and meet in the distance, much like train tracks that appear to merge far away. Within altocumulus and altostratus clouds, many droplets are supercooled. They remain liquid at temperatures below 0 degrees Celsius, sometimes down to -10 degrees or lower, until they encounter a freezing nucleus, at which point they crystallize and release latent heat. This latent heat is energy stored in the phase of water. When the droplets freeze, they quietly release that energy back into the surrounding air, altering its buoyancy, gently changing the balance of rising and sinking motion. So even within what appears to be a calm gray layer, small transformations are taking place, liquid turning to ice, heat being released, the structure of the cloud slowly adjusting to these microscopic changes. Interlude, the hygrometer, measuring invisible moisture. To complement the barometer, which measures pressure, the archive employs the hygrometer, which measures humidity. Relative humidity expresses how much water vapor is present compared to the maximum amount the air can hold at a given temperature. At 100% relative humidity, the air is saturated, and any further cooling or addition of moisture will lead to condensation. The Saussure hair hygrometer uses a bundle of human or animal hair, which lengthens as humidity increases and shortens as the air dries. This change in length is extremely small, but it is real and measurable. The hairs are connected to a delicate system of levers and pointers, so that a tiny shift in length causes a needle to move across a calibrated scale. As the air becomes more humid, the needle slowly climbs. As the air dries out, the needle slowly falls. The instrument translates the invisible behavior of water vapor into a visible motion, a gentle swing of a pointer on a dial. The psychrometer consists of two thermometers, one with a dry bulb and one with a wet bulb wrapped in a moist wick. As water evaporates from the wet bulb, it cools. The rate of evaporation, and therefore the amount of cooling, depends on how dry the surrounding air is. If the air is very dry, evaporation is rapid, and the wet bulb cools significantly, showing a lower temperature than the dry bulb. If the air is already moist, evaporation is slower, and the temperature difference between the two bulbs is smaller. By comparing these two readings, the dew point can be calculated. The dew point is the temperature at which air becomes saturated and clouds or fog begin to form. In the archive, the dew point is treated as a threshold, a quiet dividing line between invisible vapor and visible cloud. Above the dew point, water remains unseen, dispersed as vapor. At and below the dew point, that vapor begins to gather, to condense onto particles, to appear as mist, as cloud, as droplets forming on cool surfaces. The hygrometer and the psychrometer are therefore instruments that listen to moisture not with sound, but with hair, with wicks, with glass and mercury and scales, quiet translators of the air's hidden water into numbers on a page. Chapter 3. The low Étage, surface to 6,500 feet. We now descend to the lowest layer of the troposphere, the boundary layer where the atmosphere directly meets the surface of the Earth. This is the layer that touches forests and oceans, fields and cities, mountains and highways. It is the part of the atmosphere that people live inside of every day, often without noticing its structure. Here the air is dense and heavy compared to the layers above. It is often moist, carrying the breath of plants, the evaporation from lakes and seas, and the invisible exhaust of human industry. It is strongly influenced by everything that lies beneath it. Hills and valleys, rivers and rooftops, deserts and shorelines. The clouds of the low Étage are typically thicker and darker at their bases than those above. Because they are closer to the ground, their shadows move directly across human spaces, across streets, windows, fields, and water. They can make midday feel like evening, or turn a hot afternoon into a cool, subdued one with a single passing sheet. These clouds exert a direct influence on human experience. They shade cities, conceal mountains, and sometimes hide entire landscapes. They produce much of the planet's widespread rain and drizzle, quietly sustaining rivers, reservoirs, soil moisture, and the slow cycles of agriculture and vegetation. In this chapter, the archive records the main genera of the low Étage: stratocumulus, stratus, and nimbostratus. Together, they form the everyday ceiling of the world, the ordinary, often unnoticed background of weather. The genus Stratocumulus. Stratocumulus is the most frequently observed cloud type on Earth. If you look up on a cool, overcast day with a textured sky, you are likely looking at Stratocumulus. It is the workhorse of the low atmosphere, covering vast areas of the planet for long periods of time. As its name suggests, it combines aspects of stratus, layered, and cumulus, heaped. It forms lumpy fields with relatively low, flat bases, like a blanket that has been gently rumpled. From below, it often appears as a sky filled with rounded patches and rolls, more organized than chaos, but less rigid than a perfect sheet. Stratocumulus tends to form in environments where the air near the surface is moist and slightly unstable, but where a stable layer above prevents deep towering growth. This makes it a cloud of compromise. It wants to rise, but it is held down, spreading outward instead. Over oceans, it can extend for hundreds of kilometers, moderating the exchange of heat between sea and sky. The archive notes several varieties of stratocumulus that capture its different patterns. Among these we will focus on three: pellucidus, undulatus, and opacus. Each is a variation on a theme: a low, layered, lumpy cloud field, expressing subtle changes in motion and light. Stratocumulus pellucidus, SC Pel. Stratocumulus pellucidus forms a broad layer of gray and white cloud masses. They are arranged in such a way that the layer looks continuous at first glance, but careful observation reveals numerous small openings. These gaps or windows allow glimpses of the sky or higher clouds above. The key feature of Perlucidus is these openings. They are not large enough to make the sky truly broken, but they are distinct enough to puncture the monotony of the layer. They can appear as irregular holes, channels, or sometimes as a loose grid of small, almost geometric spaces between the cloud elements. Physically, these openings represent areas of descending air where clouds have thinned or dissipated. Where the air sinks slightly, it warms and dries, causing droplets to evaporate and leaving a clear patch. Where the air rises, the condensation is maintained, preserving the cloud. From the perspective of the archive, each gap is a local anomaly in the otherwise continuous layer. Each separate patch of stratocumulus records slightly different conditions of temperature, humidity, and vertical motion. The sky, in this case, is a mosaic of similar but not identical microenvironments. On the ground, a person walking under stratocumulus perlucidus may experience alternating patches of shade and soft light. The sun may appear briefly through a thinner zone, then disappear again behind thicker parts of the field. The result is a sky that feels restless but not dramatic, a dynamic ceiling that subtly changes from minute to minute. Stratocumulus undulatus, SCUND. Stratocumulus undulatus appears in parallel rows or wave-like patterns. Seen from below, these patterns resemble a gray ocean frozen above the observer. The cloud elements line up in bands, often stretching across a large portion of the sky. These waves form when layers of air at slightly different speeds or directions slide past each other, creating gentle oscillations. Where the air moves upward along these waves, cloud forms. Where it moves downward, cloud thins or vanishes. The result is a repeating pattern, like ripples on a pond or furrows in a plowed field. The spacing between the waves reflects wind speed and characteristics in the planetary boundary layer. Closer spacing can indicate certain stability conditions, while wider spacing suggests a different vertical structure. For the archive, the regularity of undulatus serves as a kind of seismograph of the invisible motions of the lower atmosphere. From below, an observer may feel as if they are lying at the bottom of an empty, shallow sea, looking up at its surface from underneath. The waves overhead do not move quickly. They often seem almost fixed, shifting only gradually over time. The entire scene is calm, structured, and hypnotic. See Stratocumulus opacus, SCOPA. Stratocumulus opacus forms a heavy, continuous sheet of dark gray CLO. UD. It is thick enough to block the sun completely, with little or no sign of where the sun's disk might be. The cloud details may still be visible as subtle lumps and rolls, but the overall impression is one of solid cove. Rage. Under such a layer, the world feels enclosed and dim. Light is present, but it is diffuse, soft, and low in contrast. Shadows are either very faint or entirely absent, and colors on the ground appear muted. This kind of sky is common on cool, damp days, especially ahead of large-scale weather systems. Sometimes light rain or drizzle may fall from Stratocumulus opacus, though often it simply hangs as a dry, dark ceiling. It can persist for many hours, creating a sense of time slowed down and compressed beneath a uniform roof. For the archive, Stratocumulus opacus is a cloud of coverage in MO duration. It rarely brings extremes, but it shapes the mood of entire regions by filtering light and marking the presence of stable, moist air near the surface. In climates where such skies are frequent, they define the visual memory of anti-seasons. 2. The genus Stratus. Stratus comes from the Latin sternera, meaning to spread out. True to its name, stratus spreads as a uniform layer, often appearing closer to fog than to the more sculpted forms of other clouds. It is the simplest and most uniform of cloud forms. These clouds often form when a shallow layer of cool, moist air is trapped near the surface, with warmer your air above. In such conditions, turbulence mixes moisture evenly, but not deeply, forming a wide-spread sheet. The sky becomes a single, continuous tone with little tour or detail. Stratus is frequently associated with calm winds and stable conditions, particularly in the early morning or during cool seasons. It can form from the gradual lifting of fog or from the lowering of higher cloud layers. In coastal regions, stratus can drift inland from a cool ocean, bringing gray, featureless days. Stratus nebulosus, St. Stratus nebulosus is a featureless gray layer. It produces an overcast sky with no distinct forms, ripples or patterns. The cloud base may appear smooth and uniform as if the sky has been painted with a single soft brush. When stratus nebulosus descends to ground level, it is recorded as fog. In this state, the cloud is no longer something to be looked at from below. It becomes the medium rough which one moves. Terrain, structures, and vegetation are wrapped in a low uniform cloud, and visibility is significantly reduced. Fog reduces visibility and dampens sound. Distant noises, such as traffic or footsteps, are absorbed or scattered, creating a muffled acoustic environment. Familiar landscapes become strange. Edges are softened, distances are obscured, and the world feels smaller and more enclosed. Within the archive, stratus nebulosus is cataloged as a cloud of erasure. It removes sharp boundaries, reduces contrast, and simplifies scenes. It is not a cloud of spectacle, but of concealment, quietly editing what can be seen and heard at the surface. Stratus fractus, Stratus fractus consists of irregular shreds or fragments of cloud moving beneath a main cloud deck. These torn pieces are often low, ragged, and quickly changing. They form a ragged underlayer drift in swift, uneven patterns. They are often associated with unsettled weather and rapidly changing conditions near the surface. As rain falls from higher clouds, evaporative cooling and gusty winds can create pockets of saturated air below. In these pockets, stratus fractus appears and disappears, forming new shapes every few seconds. These scud clouds can sometimes appear ominous from the ground, especially when racing by at low levels. They may rise, twist, or stretch along gust fronts, giving the impression of turmoil and motion. However, they are usually transient, reactive features rather than the core of the storm itself. In the archive, stratus fractus is categorized as a cloud of transition. It signals the shifting boundary between rain-cooled air and the surrounding environment. Its fleeting shapes remind the observer that the atmosphere near the surface is never entirely still, even on days that appear quiet from a distance. 3. The genus Nimbostratus. Nimbostratus is the primary genus associated with steady, widespread rainfall. Its name combines nimbus, meaning rain, and stratus, meaning lay. Together, they describe a deep, featureless cloud that can rain for many hours. Nimbostratus appears as a dark, amorphous sheet, often with diffuse, poorly defined lower boundaries. Its base may be hidden behind lower scud, or simply blurred by falling precipitate. Ion. From below, it often looks like a uniform gray curtain stretched across the sky. It is thick enough to completely blot out the sun. Even at midday, the light under nimbostratus can feel like early morning or late evening. Colors become flat, and the horizon seems to shrink beneath a heavy lid. Below the main layer, ragged stratus fractus may hang, further obscuring the sky. These low fragments drift and deform in the rain-cooled air, creating a layered, multi-level gloom. Together, the main deck and the lower scud form a complex, multi-tier structure. Unlike the towering cumulonimbus that produces intense, localized downpours and thunderstorms, nimbostratus is associated with gentle but persistent precipitation spanning large areas. The rain may not be violent, but it is tenacious, sometimes lasting an entire day or more. Snow can also fall from nimbostratus in colder conditions, replacing the sound of rain with soft, accumulating quiet. In the archive, such clouds are recorded as structures of endurance. They represent the steady, patient return of atmospheric moisture to the surface. Rather than a single dramatic event, nimbostratus embodies the slow work of climate, supplying rivers, feeding soils, and replenishing groundwater. It is a guiding observation of the archive that the lower the cloud, the more it reflects the character of the earth beneath it. High cirrus is shaped primarily by the large-scale flow of the atmosphere and the cold of upper levels. Its details are written by jet streams, temperature gradients, and distant either systems. Low stratus and stratocumulus, by contrast, are influenced by ocean temperatures, forests, cities, and terrain. They carry the imprint of coastlines, mountain ranges, and heat islands. In this way, the low Étage acts as a mirror, revealing the geography and human activity beneath. Interlude, the anemometer, the vane, and the rain gauge. To measure the movement of air, the archive employs the anemometer and the wind vane. To measure the return of water to the surface, it uses the rain gauge or pluviometer. These simple instruments translate invisible flows into numbers and records. The Robinson Cup anemometer uses 4 hemispherical cups mounted on horizontal arms. As wind strikes the concave side of each cup, it exerts more force than on the convex side, causing the assembly to spin around a central shaft. The faster the wind, the faster the cups are. The rate of rotation is proportional to wind speed and can be translated into units such as meters per second or kilometers per hour. Historically, mechanical counters or electrical pulses were used to record these rotations over time. The result is a continuous log of how the wind has behaved, gusty, calm, or steady. The wind vane, often placed at the top of a mast, aligns with the wind. It consists of a fin or arrow that pivots freely, pointing toward the direction from which the air is coming. It indicates direction rather than speed, telling us whether the wind is from the north, south, east, west, or some point in between. Together, the anemometer and vane provide a simple but powerful description of the wind at a location. They tell the archive not only how fast the air is moving, but from where it arrives. This information can be linked with cloud observations to understand why certain formations appear and how they travel. To quantify rainfall, the archive employs the pluviometer or rain gauge. A common design uses a collecting funnel leading into a narrow inner tube. The funnel has a known area, and the tube has a smaller cross-section. Because the area of the funnel is larger than that of the inner tube, small amounts of rain are effective. Easily amplified. A thin layer of rainfall spread over the funnel's surface becomes a deeper column in the tube, making measurement more precise. A calibrated scale or measuring cylinder allows the observer to read the ACC, accumulated amount. Each millimeter collected in the gauge corresponds to 1 liter of water distributed over a square meter of ground. This simple relationship connects the tiny volume in the tube to the much larger surface area AR on the station. It turns a small local sample into a meaningful estimate of how much water has fallen over the landscape. In extended observations, these simple measurements accumulate into multi-year records of local climate and hydrological balance. They show wet years and dry years, seasonal patterns, and long-term trends. When combined with cloud logs, they allow the archive to link specific sky conditions with actual returns of Étage to the surface. Chapter 4: The Clouds of Vertical Development. Up to this point, we have categorized clouds primarily by the étage or vertical level in which they reside. We have spoken of high, middle, and low levels as if clouds lived in separate floors of an atmospheric building. However, there exists a class of clouds that defy such neat boundaries. These are the clouds of vertical development. They begin as shallow formations near the surface and grow upward, sometimes spanning the full depth of the troposphere. They are the visible signatures of strong convection, air that rises vigorously from the surface into the colder air above. In many cases, these clouds start small as harmless puffs on a fair day. Given the right conditions, enough moisture, enough instability, they can grow into towering structures with deep, complex internal circulations. In doing so, they link the lowest air directly with the top of the weather layer. The archive groups these clouds under two main genera, cumulus and cumulonimbus. Cumulus covers the family of heaped, detached clouds with varying vertical extent. Cumulonimbus represents their most developed, storm-bearing form. The genus Cumulus. Cumulus, from the Latin for heap, represents the visible expression of convection, warm air rising from the surface. Each cumulus cloud marks the location of a rising thermal, a column of buoyant air lifting away from the ground. From a distance, a field of cumulus looks like a map of invisible upward currents. These clouds typically have sharp, well-defined outlines and relatively flat bases. The base marks the lifting condensation level, where rising air has cooled enough to become saturated and begin forming droplets. Above this level, the cloud can grow upward as long as the air remains buoyant relative to its surroundings. Within the genus Cumulus, the archive distinguishes several species based on vertical extent: Humulus, Mediocris, and Congestus. Each represents a stage in the life cycle of convection, from gentle thermals to deep, towering updrafts. We will follow this progression step by step. Cumulus humulus, hum. Cumulus humulus consists of small, flattened clouds wider than they are tall. They often appear on quiet, fair-weather days, scattered across a blue background. Their tops are bright and well-defined, while their bases form a nearly uniform level in the sky. In the archive, they are considered fair-weather clouds, indicating limited vertical motion. The atmosphere aloft is stable enough that rising thermals quickly lose buoyancy and stop growing upward. As a result, the clouds remain shallow, like low hills rather than high mountains. They mark the locations where surface heating has initiated shallow thermals. Fields, roads, and urban areas may warm unequally, creating small patches of rising air. Where these thermals reach the condensation level, cumulus pops into existence. However, a stable layer aloft prevents further growth. The rising air encounters a region where its temperature is no longer much warmer than the surrounding air. At this point, the thermal spreads out, and the cloud stops rising, remaining modest and well-behaved. From the ground, cumulus can be reassuring. They signal that the surface is warm and that some convection is occurring, but they rarely bring rain. They are sometimes called good weather clouds, a staple of calm summer afternoons. Cumulus mediocris CU-Med. Cumulus mediocris exhibits moderate vertical extent. The tops show more pronounced protrusions, somewhat resembling small cauliflower heads. The cloud is noticeably taller than cumulus, though still not towering. These clouds indicate stronger convection and a less restrictive environment aloft. The rising air parcels can penetrate higher before losing buoyancy. As they do, the tops of the clouds develop more texture and structure, hinting at possible further growth. Given sufficient moisture and instability, cumulus mediocris may continue to grow and transition into more significant forms. They can serve as a precursor to deeper convective development later in the day. The archive often notes them as potential clouds, signals of what might come if conditions continue to evolve. On some days, however, cumulus mediocris remains in a kind of equilibrium. They rise, flatten slightly, and dissipate, only to be replaced by new ones. This continuous cycle marks a dynamic but not extreme atmosphere, where convection is active but capped. Cumulus congestus CU-Con. Cumulus congestus is towering cumulus. These clouds can reach several kilometers in height, with sharply defined, bright white summits. From a distance, they resemble great columns or towers rising from a shared base level. Their bases remain relatively dark and flat, indicating the lifting condensation level. From there, strong updrafts carry moisture upward into ever colder layers, building the cloud vertically. The contrast between the dark base and bright top makes cumulus congestus visually striking. Within such a cloud, strong updrafts can transport vast amounts of water upward every minute. Droplets and ice particles are lifted, frozen, melted, and lifted again in complex internal circulations. This vigorous mixing prepares the way for the eventual transition to cumulonimbus, if conditions allow. The vertical column acts as a conduit, redistributing heat and moisture between the surface and higher layers. As water vapor condenses and freezes, latent heat is released, warming the rising air and helping it continue its ascent. In this way, the cloud itself becomes part of the engine that drives further convection. In the archive, cumulus congestus is recorded as a threshold cloud. It stands at the border between fair-weather cumulus and full storm clouds. Its presence suggests that the atmosphere has enough energy to support deeper, more organized convection. 2. The genus Cumulonimbus. Cumulonimbus is the ultimate expression of vertical development in the troposphere. These clouds often extend from near the surface all the way up to the tropopause, the upper boundary of the weather lay. They are tall enough to connect the warm lower atmosphere directly with the cold upper regi. A fully developed cumulonimbus cloud contains intense updrafts, downdrafts, and complex internal structures. Within it, water can exist simultaneously as vapor, liquid, and ice, undergoing rapid transformation. Lightning, thunder, heavy rain, hail, and strong winds are all possible manifestations of its internal dynamics. The archive distinguishes stages in the life of cumulonimbus, focusing on its crown and anvil. Two important documented forms are cumulonimbus calvus and cumulonimbus capillatus, the latter often associated with a well-developed anvil or incus. Cumulonimbus calvus, c. Bical. In the cumulonimbus calvus stage, the top of the cloud begins to lose some of its sharpness. The previously distinct cauliflower structure of a congestus cloud becomes smoother and redomed. This change is subtle at first, but it signals an important internal shift. At these upper levels, water droplets at the summit begin to freeze into ice crystals. The transition from liquid to ice releases latent heat, which further energizes the updraft. This process is essential to the full development of the storm. As glaciation progresses, the cloud top brightens and spreads. The once crisp edges soften into a wider, more diffuse mass. To the trained observer, this marks the moment when the cloud is no longer just a deep cumulus, but a genuine cumulonimbus. This transition marks the onset of glaciation at upper levels, accompanied by the release of latent heat. From this point, the cloud's evolution can accelerate, leading toward the mature stage. With an anvil, updrafts may reach their maximum strength, and lightning may begin to appear within the owing structure. Cumulonimbus capillatus and the anvil CB cap. Cumulonimbus capillatus is the mature form. At this stage, the cloud reaches the stable layer near the tropopause and can no longer or grow vertically. Its top spreads outward horizontally, constrained by the stability above. This spreading top forms an anvil-shaped extension, known as the incus. From a distance, the anvil can appear as a broad, flat platform, extending sideways far from the main updraft column. Its edges may be fibrous or feathered, reflecting the presence of ice crystals. This anvil is composed predominantly of ice crystals. High-level winds may shear and stretch it horizontally, producing a vast plume that can extend far from the original updraft region. Sometimes, multiple storms can share a merged anvil, creating a continuous high cloud shield. Beneath the anvil and within the core of the cloud, heavy rain, hail, and lightning may occur. Strong downdrafts develop as cooled, rain-cooled or hail-laden air descends toward the surface. When this descending air reaches the ground, it can spread outward as a gust front, bringing sudden wind shifts and temperature drops. In extreme cases, strong downdrafts and gust fronts spread outward from the storm, modifying conditions at the surface over large areas. Visibility can drop in heavy rain or blowing dust, and rapid pressure changes can be recorded by barometers. The storm becomes not just a feature of the sky but an active agent shaping the environment below. In the archive, cumulonimbus is noted not only as a storm cloud, but as a vertical bridge. It carries moist, warm air from the surface to the cold upper troposphere, where it is transformed into ice and then returned to the surface as precipitation. Through this vertical exchange, cumulonimbus plays a central role in the global transport of heat and water. Interlude, the Glossary of the High Archive. To conclude our extended documentation, we return to the glossary, the precise vocabulary the archive uses to describe atmospheric phenomena. Each term is a compact record of a more complex process. a small label attached to a much richer story. Aerosol, a suspension of fine solid particles or liquid droplets in air, acting as nuclei for cloud droplets. Each aerosol particle can serve as the starting point for a droplet linking surface processes, dust, sea spray, pollution, to cloud formation aloft. Albedo, the fraction of incoming radiation reflected by a surface. Bright clouds and snowfields have high albedo, returning much of the sun's energy to space, while dark oceans and forests absorb more. Boundary layer, the lowest portion of the atmosphere directly influenced by the surface, where friction, heating, and moisture fluxes are strongest. It is in this layer that low clouds form, where turbulence mixes heat and humidity, and where human activity leaves its clearest imprint. Condensation level, the altitude at which rising air cools enough to become saturated, forming visible cloud bases. It marks the transition from invisible water vapor to visible cloud, turning thermals into cumulus with a sharp, flat bottom. Convection, vertical transport of heat and moisture, often visible as cumulus clouds. It is the process by which the surface communicates its warmth to higher layers, creating thermals, updrafts, and ultimately storms. Dew point, the temperature at which air becomes saturated and condensation begins. When the air cools to its dew point near the surface, dew forms on grass and leaves. When this occurs at height, clouds appear. Evapotranspiration, combined evaporation from soil and water surfaces and transpiration from plants, supplying moisture to the atmosphere. This process links the biosphere and hydrosphere with the atmosphere, feeding low-level clouds with water vapor. Hygroscopic, having the ability to attract and hold water molecules from the surrounding environment. Hygroscopic particles, such as sea salt, make especially effective cloud condensation nuclei. Inversion, a layer where temperature increases with height, inhibiting vertical motion and trapping clouds or pollutants below it. Under an inversion, smoke, haze, and low clouds can accumulate, while the air above remains clear. Isobar, a line connecting points of equal atmospheric pressure on a weather map. Isobars reveal the shapes of high and low pressure systems and indicate where winds will be strong or weak. Latent heat, energy absorbed or released during phase changes of water, such as evaporation, condensation, freezing, or melting. Latent heat powers many atmospheric processes, turning phase changes into fuel for convection and storms. Lapse rate, the rate at which temperature decreases with height in the atmosphere, often around 6.5 degrees Celsius per kilometer in the standard atmosphere. Comparing the actual lapse rate to this standard helps determine stability and the likelihood of convection. Mesosphere, the region above the stratosphere where rare noctilucent clouds can occasionally form, beyond the scope of this tropospheric log. These clouds glow high above, reflecting sunlight long after sunset, hinting at processes far above ordinary weather. Orographic lift, the forced ascent of air over terrain such as mountains, leading to cooling and potential cloud formation. On the windward side of ranges, this lift produces clouds and precipitation. On the leeward side, air descends and dries. Troposphere, the lowest major layer of the atmosphere, containing most of its mass and nearly all of its weather systems. It is the stage upon which all the clouds in this archive perform. Virga, precipitation that falls from a cloud but evaporates or sublimes before reaching the ground, appearing as faint streaks beneath the cloud base. Virga marks the boundary between the humid interior of a cloud and the drier air below. Chapter 5. The Global Circulation, the great engine. We have been looking closely at individual clouds, almost as if they were separate characters in a story. Now we will step back and widen the frame. The clouds we see are not drifting at random. They are passengers inside a much larger, quieter machine. The atmosphere is not just a sky full of vapor. It is a global heat engine, always running, always adjusting, always moving energy from one place to another. Most of the time we do not notice this engine. We only notice its subtle results. A breeze at the window, a sudden shower, a clear day that feels strangely still. In this chapter we will sit with that engine. We will trace how air rises, how it sinks, and how it slides across the planet in slow looping circuits. We will focus on three ideas: rising warm air, descending cool air, and the gentle turning caused by the spinning Earth. We begin at the equator, where sunlight is the most direct, and the atmosphere is always being quietly heated from below. The Hadley Cell. Near the equator, the sun's energy is intense and persistent. Day after day, it warms the surface, land, ocean, and everything in between. The air that touches this warm surface becomes warm as well. Warm air is light, and it does what light things do. It rises. Imagine a column of air at the equator. As the sun heats it, this column slowly swells and lifts, like a soft, invisible plume. Moisture from the ocean and from tropical forests is carried upward with it. The air becomes humid, buoyant, and unstable, ready to climb. As this air rises, it expands into the lower pressure of higher altitudes. When a gas expands, it cools even without losing heat to its surroundings. This is called adiabatic cooling. It is a quiet process, but you can imagine it as the air slowly relaxing and spreading out, losing some of its ability to hold water vapor. As it cools, the invisible vapor begins to condense into droplets and ice crystals. This is where the towering cumulonimbus and deep cumulus congestus clouds of the tropics are born. From the ground, these clouds look like vast mountains. From above, they look like soft, boiling towers, punching upward toward the edge of the troposphere. High above, at roughly 50,000 feet, the rising air reaches a kind of ceiling. It can go no higher because the surrounding air is no longer lighter than it is. At this level, the rising motion slows, and the air spreads out horizontally, like water reaching the rim of a basin. From this ceiling, the air begins to move away from the equator, both northward and southward. It is no longer rising. Instead, it is flowing outward, forming high-altitude winds that travel toward the subtropics. On weather maps, this layer is sometimes revealed by graceful streaks of cirrus and cirrostratus, tracing the path of the upper-level flow. As the air moves away from the equator, it slowly cools. The warmth it once carried from the tropics is gradually radiated away into space or mixed with cooler air. Over time, this air becomes denser and heavier. Around 30 degrees north and south of the equator, a change occurs. Here, the cooled air begins to descend. The long, slow fall of this air defines the other half of the loop we call the Hadley Cell. As the air descends, it is compressed by the increasing pressure of the lower atmosphere. Compressed air warms. This warming dries out the descending air, reducing its humidity and inhibiting cloud formation, especially low and middle clouds. At the surface beneath this descending branch, a belt of high pressure forms. These are the subtropical highs. They tend to bring clear skies, gentle winds, and dry conditions. Many of the world's great deserts lie under this descending arm of the Hadley Cell. The Sahara, the Arabian Desert, and regions of Australia and southwestern America all live beneath this quiet downward motion. Here, the sky is often bare of low clouds, and the sun's path across the sky is recorded on the land as heat and dryness. In this way, the Hadley Cell forms a huge loop. Warm, moist air rises at the equator, flows outward at high altitude, sinks at the subtropics, and returns near the surface back toward the equator. It is a slow, planetary scale breathing pattern, always inhaling heat at low latitudes and exhaling it toward higher ones. 2. The Coriolis effect. So far, we have imagined the air moving north and south in straight lines, like water flowing along channels carved from equator to pole. But the Earth does not stand still beneath this moving air. Spins. Because the Earth rotates, anything moving long distances over its surface appears to curve. This apparent turning is called the Coriolis effect. It is not a force you can touch, but it is a pattern you can see in the paths of winds and currents across the globe. In the northern hemisphere, this apparent deflection bends moving air to the right of its path. In the southern hemisphere, it bends moving air to the left. The effect is gentle, but over thousands of kilometers, its influence becomes unmistakable. Consider a parcel of air flowing from the subtropics back toward the equator near the surface. If the planet were not rotating, this air would move straight south in the northern hemisphere or straight north in the southern hemisphere. Instead, the Coriolis effect turns these flows. In the northern hemisphere, air moving toward the equator is turned to the right. The result is a steady flow from the northeast toward the southwest, the northeast trade winds. In the southern hemisphere, air is turned to the left, forming the southeast trade winds. These trade winds meet near the equator in a zone of convergence. Here, the surface winds are often weak, and the air is rising. This region is sometimes known as the intertropical convergence zone. Sailors once feared these calm areas, calling them the doldrums, a place where ships could stall for days in weak and shifting breezes. Farther from the equator, between about 30 and 60 degrees latitude, the pattern reverses. Chapter 5. The Global Circulation, the Great Engine. We have been looking closely at individual clouds, almost as if they were separate characters in a story. Now we will step back and widen the frame. The clouds we see are not drifting at random. They are passengers inside a much larger, quieter machine. The atmosphere is not just a sky full of VIII. It is a global heat engine, always running, always adjusting, always moving energy from one place to another. Most of the time we do not notice the Étage. We only notice its subtle results. A breeze at the window, a sudden shower, a clear day that feels strangely still. In this chapter we will sit with that engine. We will trace how air rises, how it sinks, and how it slides across the planet in slow looping circuits. We will focus on three ideas: rising warm air, descending cool air, and the gentle turning caused by the spinning Earth. We begin at the equator, where sunlight is the most direct, and the atmosphere is always being quietly heated from below. The Hadley cell. Near the equator, the sun's energy is intense and persistent. Day after day, it warms the surface, land, ocean, and everything in between. The air that touches this warm surface becomes warm as well. Warm air is light, and it does what light things do. It rises. Imagine a column of air at the equator. As the sun heats it, this column slowly swells and lifts, like a soft, invisible plume. Moisture from the ocean and from tropical forests is carried poured with it. The air becomes humid, buoyant, and unstable, ready to climb. As this air rises, it expands into the lower pressure of higher altitudes. When a gas expands, it cools even without losing heat to its surroundings. This is called adiabatic cooling. It is a quiet process, but you can imagine it as the air slowly relaxing and spreading out, losing some of its ability to hold water vapor. As it cools, the invisible vapor begins to condense into droplets and ice crystals. This is where the towering cumulonimbus and deep cumulus congestus clouds of the tropics are born. From the ground, these clouds look like vast mountains. From above, they look like soft, boiling towers, punching upward toward the edge of the troposphere. High above, at roughly 50,000 feet, the rising air reach a kind of ceiling. It can go no higher because the surrounding air is no longer lighter than it is. At this level, the rising motion slows, and the air spreads out horizontally like water reaching the rim of a basin. From this ceiling, the air begins to move away from the equator, both northward and southward. It is no longer rising. Instead, it is flowing outward, forming high-altitude winds that travel toward the subtropics. On weather maps, this layer is sometimes revealed by graceful streaks of cirrus and cirrostratus, tracing the path of the upper-level flow. As the air moves away from the equator, it slowly cools. The warmth it once carried from the tropics is gradually radiated away into space or mixed with cooler air. Over time, this air becomes denser and heavier. Around 30 degrees north and south of the equator, a change occurs. Near the cold air begins to descend. The long, slow fall of this air defines the other half of the loop we call the Hadley cell. As the air descends, it is compressed by the increasing pressure of the lower atmosphere. Compressed air warms. This warming dries out the descending air, reducing its humidity and inhibiting cloud formation, especially low and middle clouds. At the surface beneath this descending branch, a belt of high pressure forms. These are the subtropical highs. They tend to bring clear skies, gentle winds, and dry conditions. Many of the world's great deserts lie under this descending arm of the Hadley cell. The Sahara, the Arabian Desert, and regions of Australia and southwestern America all lie beneath this quiet downward motion. Here, the sky is often bare of low clouds, and the sun's path across the sky is recorded. On the land is heat and dryness. In this way, the Hadley cell forms a huge loop. Warm, moist air rises at the equator, flows outward at high altitude, sinks at the subtropics, and returns near the surface back toward the equator. It is a slow, planetary scale breathing pattern, always inhaling heat at low latitudes, and exhaling it toward higher ones. 2. The Coriolis effect. So far, we have imagined the air moving north and south in straight lines, like water flowing along sea panels carved from equator to pole. But the Earth does not stand still beneath this moving air. Spins. Because the Earth rotates, anything moving long distance over its surface appears to curve. This apparent turning is called the Coriolis effect. It is not a force you can touch, but it is a pattern you can see in the paths of winds and currents across the globe. In the northern hemisphere, this apparent deflection NDS moving air to the right of its path. In the southern hemisphere, it bends moving air to the left. The effect is gentle, but over thousands of kilometers, its influence becomes unmistakable. Consider a parcel of air flowing from the subtropics back toward the equator near the surface. If the planet were not rotating, this air would move straight south in the northern hemisphere or straight north in the southern hemisphere. The Coriolis effect turns these flows. In the northern hemisphere, air moving toward the equator is turned to the right. The result is a steady flow from the northeast toward the southwest, the northeast trade winds. In the southern hemisphere, air is turned the left, forming the southeast trade winds. These trade winds meet near the equator in a zone of convergence. Here, the surface winds are often weak and the air is rising. This region is sometimes known as the intertropical convergence zone. Sailors once feared these calm areas, calling them the doldrums, a place where ships could stall for days in weak and shifting breeze. Yes. Farther from the equator, between about 30 and 60 degrees latitude, the pattern reverse. Yes. Air now flows toward the poles near the surface and is again bent by the Coriolis EFF. CT. This produces the westerlies, winds that blow from the west toward the east in both hemispheres. The westerlies are responsible for pushing large sheets of cloud, altostratus, nimbostratus, and widespread stratiform layers across entire ocean basins and continents. A storm born over the Pacific can travel day by day into the interior of North America. A low-pressure system off the Atlantic can carry its cloud shield into Europe, guided by these relentless upper-level and mid-level flows. High above, delicate filaments of Cirrus vibratus and Cirrus uncinus often mark the paths of these jet-like streams. They stretch like fine threads, aligned with the wind, tracing the invisible rivers of air that circle the globe. Watching them drift across the sky, one is watching the handwriting of the planet's rotation translated in to cloud. The Hadley cell, the Coriolis effect, the trade winds, and the westerlies are all parts of a single vast circulation. They do not shout. They whisper in the slow movement of pressure systems and the patient march of cloud decks from horizon to horizon. Chapter 6. The Microscopic Archive. The Physics of the Drop. Inside a single cloud, millions of tiny stories are unfolding at once. Each droplet has a beginning, a middle, and an end. To extend our record, we will follow a single raindrop, from its first fragile existence as moisture attached to a tiny particle, to its growth through collisions, and finally to its descent as precipitatio. This process, known as collision coalescence, is the quiet biography of a raindrop. Inside a thick nimbostratus layer, this story repeats over and over, filling the archive with countless similar entries. We will begin where every droplet begins, with a solid particle so small we cannot see it with the naked eye. The architecture of the nucleus. Pure water vapor does not easily condense into droplets on its own. It prefers to gather around something solid or at least something already formed. That something is called a cloud condensation nucleus, or CCN. A CCN is a tiny particle, often much smaller than a red blood cell. Yet this microscopic speck can determine when and where a droplet will form. Different types of particles make different kinds of droplets and therefore different kinds of clouds. One important source of CCN is salt. When waves break, they throw small bubbles into the air. As these bubbles burst, they release minute salt particles into the atmosphere. These salt particles are hygroscopic. This means they have a natural attraction to water molecules, almost like a gentle magnetism. Water vapor in the surrounding air is more likely to cling to them, forming the first tiny liquid shells that will grow into ClO(UD) droplets. Another common nucleus is kaolinite, a clay mineral often found in desert dust. Dust storms can carry kaolinite thousands of kilometers, lifting it into the higher layers of the troposphere. Up there, temperatures are low, and kaolinite's crystalline structure becomes important. The lattice of kaolinite is similar in shape to that of ice. Water molecules can arrange themselves on its surface in an orderly way, mimicking the structure of a TI, New York ice crystal. In this way, kaolinite can serve as an efficient ice nucleus, helping to seed the first ice particles in high-level clouds of the upper Étage. Forests provide yet another CLA-SS of particles. Trees release organic compounds called terpenes into the air. These molecules react with sunlight and other gases to form tiny aerosol particles. Over large forested areas, these aerosols can create a faint bluish haze, especially visible in mountain ranges such as the Blue Ridge. Within this haze, cloud droplets can form, giving rise to gentle layers of stratus nebulosus and of our low-level clouds. The living landscape thus writes itself into the sky, leaving a trace in the microstruct of each droplet. So within a single cloud, we may find sea salt particles from distant oceans, clay dust from deserts half a world away, and organic aerosols from nearby forests. Each nucleus carries a fragment of Earth's surface into the atmosphere. Together, they form the microscopic scaffolding on which clouds are built. 2. The descent and the terminal velocity. Inside a cumulus mediocris cloud, air is rising, but not as violently as in towering thunderstorms. Small droplets are carried upward and kept aloft by gentle updrafts. As long as a droplet is small enough, it can stay suspended, floating in drifting as if weightless. A typical cloud droplet is extremely small, often around a fraction of 1/100th of a millimeter in diameter. At this size, its fall speed is only about 1 centimeter per second. At that rate, a droplet would take many minutes to fall a short distance, and in the process, it would likely evaporate into the surrounding air before ever leave the base of the cloud. But droplets inside a cloud are not alone. They are surrounded by millions of others, all moving, colliding, and interacting with the turbulent motions of the air. When droplets collide, several things can happen. They might bounce apart, they might temporarily stick and then separate, or they might merge into a single larger droplet. When they merge, we say they coalesce. Each successful coalescence creates a droplet slightly larger than before. As a droplet grows, its fall speed, its terminal velocity, increases. This means it begins to slip downward through the cloud fosse than its smaller neighbors. When a droplet reaches a size of about 1 millimeter in diameter, its terminal velocity can increase to roughly 4 meters per second. At this speed, it can fall through the cloud and reach the ground before it has time to evaporate. The droplet is no longer part of the suspended cloud. It has become precipitation. Within the archive, we can imagine a small notation, a status change. A droplet that was once recorded under suspension is moved into the category of precipitation. A microscopic event, a few successful collisions, has changed the outcome for that droplet. As more droplets follow the same path, the cloud's character changes. What was once a diffuse field of tiny suspended droplets becomes a rainy cloud, shedding mass toward the surface. If the process continues, the cloud may even thin or dissipate as water is removed and deposited on the ground. In thick nimbostratus, this process is widespread and gentle, producing steady, soaking rain. In cumulonimbus, the same idea occurs under more extreme conditions with stronger FTS, larger drops, and sometimes hail. In both cases, the story begins with a nucleus and ends with a fall to Earth, ed by gravity and shaped by collisions. Chapter 7. The Nephoscope and the Victorian Record. Before orbiting satellites and digital sensors, the sky was observed by patients, and by carefully designed instruments of glass, metal, and paper. The archive, in its mechanical wing, preserves not only the clouds themselves but the tools used to measure them. In the 19th century, observers watched the sky for hours, recording the motion of clouds, the brightness of the sun, and the passage of veils and shadows. They worked with simple devices that translated the shifting sky into lines, burns, and numbers. Two of these instruments are central to our record: the Nephoscope and the sunshine recorder. The Feynman Nephoscope. The Feynman Nephoscope was invented in the late 1800s. Its purpose was to measure the speed and direction of clouds, even when their height was unknown. It offered a way to track the motion of the upper air using nothing more complicated than a mirror, some markings, and a careful eye. The instrument consisted of a flat disc with a polished black glass surface. On this surface were etched concentric circles, like ripples on a pond, along with a compass rose marking the cardinal directions. The dark glass turned the sky into a reflected field, making clouds easier to track. To use the Nephoscope, the observer would stand over the instrument and choose a particular cloud, perhaps a small patch of cirrocumulus lenticularis. They would position themselves so that the reflection of this cloud appeared at the very center of the mirror, aligned with the innermost circle. Then they would watch as the cloud's reflection drifted across the mirror. As the cloud moved overhead, its reflection crossed from one circle to the next. By using a stopwatch, the observer could measure how long it took for the reflection to travel from the center toward the outer rings. From this information, the time taken, the spacing of the circles, and the orientation of the compass marks, the observer could calculate the cloud's angular velocity. They did not need to know the exact altitude to record a meaningful measure of its motion. This was enough to build statistics about the behavior of different cloud types at different levels. Over many days, weeks, and years, such measurements accumulated. They formed an early database of upper-air winds, recorded not by balloons or aircraft, but by reflections and careful timing. Each entry was a simple pair of numbers, direction and speed tied to a date, a location, and a kind of cloud. To read these records now is to see the sky as the Victorians saw it: slow, methodical, a moving ceiling measured in degrees per minute. The Feynman Nephoscope turned fleeting clouds into stable entries in the archive, one timed crossing at a time. 2. The sunshine recorder, the Campbell-Stokes pattern. Clouds do more than move, they also filter and block the light of the sun. To capture this aspect of the sky, another instrument was developed: the sunshine recorder. One of the most widely used designs is the Campbell-Stokes recorder. This device looks deceptively simple. At its heart is a solid glass sphere, mounted carefully in a frame. The sphere acts as a universal magnifying lens, taking the parallel rays of sunlight and focusing them to a small, bright point. Behind the sphere, fitted into a curved metal holder, is a strip of specially prepared paper or card. As the sun moves across the sky, the focus point of light sweeps along this card, burning a thin track into its surface. On a perfectly clear day, this track is continuous, dark, and easy to see. When a layer of cloud passes in front of the sun, the light is dimmed. If the cloud is thin, like a cirrostratus veil, the focused light may grow weaker but not vanish. The burn on the card becomes faint but often remains present, a pale trace in the record. If a thicker cloud arrives, such as altostratus opacus, the sunlight might be reduced enough that the focal point can no longer scorch the paper. In that case, the burn line weakens further, breaks, or disappears entirely for a time. When the sun emerges again, the bright point returns and the burning resumes. When a tall, dense cumulonimbus anvil passes directly across the sun, the effect can be dramatic. The light may be completely blocked. On the card, this shows up as a clear gap, a missing segment in what might otherwise have been a continuous curve. By examining a day's card, an observer can reconstruct the history of sunshine at that station. Periods of unbroken burn indicate clear skies. Broken, intermittent marks point to passing clouds of varying thickness and type. Over months and years, these paper strips accumulate, forming a long-term record of how often the sun was visible and for how long. Without showing shapes or colors, the Campbell-Stokes recorder captures the rhythm of cloud cover, the alternation of brightness and obscuration, light and shade. In the archive, these burned cards sit alongside written logs and sketches. Together, they form a layered memory of the sky before the age of electronic sensors. Each scorch mark is a trace of the sun's path, filtered through whatever cloud happened to stand in the way on that particular day. Chapter 8: The Pressure of the Invisible Ocean. It is a founding observation of the archive that we live at the bottom of an invisible ocean of air. This ocean has weight, it presses on every surface, and it changes from hour to hour in ways that shape clouds, winds, and rain. We rarely feel this pressure directly. It does not push on us with sharp edges or sudden force. Instead, it is a constant presence like the weight of a blanket that has always been there. The archive dedicates this chapter to the measurement of that pressure. Before we can understand why clouds rise or why storms form, we must be able to say how heavy the air is, and how that weight is changing. We will examine the barometer, the early weather glass, and the way networks of instruments turned local observations into the first maps of the moving atmosphere. The invention of the barometer. In the 17th century, natural philosophers began to suspect that air itself might have weight. If this were true, it should be possible to measure that weight not directly but through its effect on a column of liquid. In 1643, Evangelista Torricelli devised the instrument that would prove this idea. He filled a long, closed glass tube with mercury, then inverted it into a dish of the same metal with the open end submerged. Some of the mercury flowed out into the dish, but a tall column remained suspended inside the tube. Torricelli observed that the height of this mercury column was not fixed. It changed slightly from day to day, rising or falling as if responding to something outside the glass. He concluded that it was the weight of the atmosphere pressing down on the exposed mercury in the dish that held the column up in the tube. When the air was heavier, when the atmospheric pressure was higher, the mercury column rose. When the air was lighter, when pressure dropped, the column fell. The barometer was thus born, a device that translates the invisible weight of air into a visible height of liquid. Torricelli wrote that we live submerged at the bottom of an ocean of air, a phrase that the archive adopts as a guiding metaphor. The barometer became the ruler held up against this ocean, recording its subtle tides and waves. 2. The climb to the mountain. To test the idea that air grows lighter with height, experiments were carried out on mountains. If the atmosphere is an ocean, then climbing upward should be like moving toward its surface, where the weight of air above us is less. In 1648, Florent Perrier, following the suggestion of Blaise Pascal, carried a mercury barometer up the Puy de Dôme in France. He made careful measurements of the mercury height at the base of the mountain and again at higher points along the climb. At the summit, the column was lower than at the bottom as Pascal had predicted. The conclusion was clear. Atmospheric pressure decreases with altitude. Higher up, there is simply less air above to exert weight. The archive records this experiment as an early vertical profile of the invisible ocean. This discovery also showed that barometers could be used not only to study weather but to estimate elevation. For a time, they served explorers and surveyors as portable altimeters, translating pressure into height above sea level. Later, their role shifted more firmly into meteorology, as observers noticed that changes in pressure over time corresponded to changes in weather. 3. The domestic weather glass. As barometers became more widely used, they slowly moved from laboratories into homes. In the 18th and 19th centuries, domestic barometers were often decorative objects, mounted in wood, brass, and glass. They hung in parlors and hallways, where visitors could see them and discuss the state of the air. Some early designs used water rather than mercury. In these weather glasses, a sealed vessel and a rising spout of liquid responded to pressure change. Yes. When atmospheric pressure fell ahead of a storm, the water in the spout would rise. When pressure increased, it would fall. These instruments were imperfect, as water expands and contracts with temperature, complicating the reading. Yet they provided a rough guide to local atmospheric activity, a simple visible cue that the air was growing lighter or heavier. Glass bulges or pinches along the vessel served as a scale, with vague labels such as stormy, rain, change, fair, and dry. Mercury barometers, building on Torricelli's design, offered more precise readings. They became standard instruments in observatories and later in weather services. In the archive, these barometers are regarded as the first reliable translators of atmospheric weight into written numbers for pressure, clouds, and forecast. By the late 19th century, systematic barometric readings were being taken at many stations. Observers recorded not only the absolute pressure but also how it changed over time, the pressure tendency. They began to notice patterns linking pressure changes with the approach or departure of weather systems. When pressure falls steadily, it often signals the arrival of a low-pressure system, a region where air is rising and clouds are thickening. Under such conditions, layers of nimbostratus or fields of deep stratocumulus may form, bringing extended cloud cover and precipitation. When pressure rises, it often corresponds to the spread of high pressure and sinking air, clearing clouds and restoring fair weather. When used together with wind observations from vanes and anemometers, barometric readings make short-term forecasts possible. A falling barometer and strengthening winds from certain directions might warn of an approaching storm. A rising barometer and calming winds might suggest the return of stable cloudless, oppressing air. Simultaneous barometric readings from many stations allow the construction of pressure maps, with isobars connecting points of equal pressure. These maps reveal the shapes of highs and lows and the tightness of their pressure gradients. The archive recognizes these early pressure charts as the first true portraits of the atmosphere as a single, connected system. The low clouds and warming world. Low-level clouds, stratus, stratocumulus, and shallow cumulus, play an important role in reflecting sunlight back into space. Because they are close to the surface and often thick, their bright tops can significantly cool the planet by easing its albedo. Recent studies suggest that changes in the amount and distribution of these low clouds can influence global temperatures. A reduction in low-level cloud cover means more sunlight reaches the surface, enhancing warming. In some analyses of the recent temperature surge, a decrease in low clouds has been noted as a contributing factor. This change may be partly driven by the warm-in atmosphere itself. As greenhouse gas-induced warming alters temperature and humidity profiles, it can also change how and here low clouds form. Reductions in certain types of pollution, such as ship exhaust and coal-burning aerosols that once acted as cloud seeds, may further reduce low cloud formation. The archive records this as a subtle feedback. As we clean the air and warm the climate, the low-lying reflectors that once shaded the surface become less common. Fewer low clouds can mean more absorbed sunlight, which in turn can further warm the surface and the boundary layer. Barometers, rain gauges, and long-term cloud logs together begin to reveal this slow rearrangement of the sky. 6. Fog is a cloud you can walk through. Among the clouds of the low Étage, fog is unique because we do not look up at it, we enter it. Fog is simply stratus that has settled to the ground, or a cloud whose base has dropped until it touches the surface. When we walk into fog, we experience directly what it would feel like to pass through a low cloud layer. The air feels slightly cooler and more humid. Tiny droplets cling to skin and hair. Visibility is reduced and the world becomes soft-edged and enclosed. In this state, the cloud is no longer just an object for remote observation. It becomes the very medium through which we Fog makes the airflow visible as wisps drift past streetlights and around buildings. The archive notes that in fog, the boundary between sky and earth temporarily dissolves. Modern satellites can distinguish low clouds and fog from higher forms by their temperature and other properties. Processed images highlight these near-surface layers, providing warnings to pilots and rivers. Even as instruments become more complex, the basic principle remains. A cloud close to the ground is both a weather event and an immediate human experience. 7. The quiet network. Barometers, anemometers, vanes, rain gauges, sunshine recorders, and cloud logs together form a quiet network of instruments. Each device measures a different aspect of the same shifting medium: pressure, motion, moisture, light, and form. Over days, their readings may seem unremarkable, small changes, small numbers. Over years and decades, patterns emerge. Trends in pressure, changes in rainfall, shifts in cloud types, alterations in fog frequency. The archive regards these cumulative records as the true memory of the atmosphere. In earlier chapters, we described individual clouds and the engines that move them. Here we have described the weight of the air itself and the instruments that made that weight visible. In future expansions, each of these instruments could be given its own dedicated log, tracing its evolution from simple glass and metal to digital sensors and orbital platforms. For now, the archive closes this chapter with a simple note. Every cloud in the log, every stratus, every cumulus, every nimbostratus, formed under a specific pressure, in a specific slice of the invisible ocean. The barometer, quietly ticking on a wall or recording in a shelter, is the marginalia that tells us how heavy the sky was when each entry was made. 6. Fog is a cloud you can walk through. Among the clouds of the low Étage, fog is unique because we do not look up at it, we enter it. Fog is simply stratus that has settled to the ground, or a cloud whose base has dropped until it touches the surface. When we walk into fog, we experience directly what it would feel like to pass through a low cloud layer. The air feels slightly cooler and more humid. Tiny droplets cling to skin and hair. Visibility is reduced and the world becomes soft-edged and enclosed. In this state, the cloud is no longer just an object for remote observation. It becomes the very medium through which we am. Fog makes the airflow visible as wisps drift past streetlights and around buildings. The archive notes that in fog, the boundary between sky and earth temporarily dissolves. Modern satellites can distinguish low clouds and fog from higher forms by their temperature and other properties. Processed images highlight these near-surface layers, providing warnings to pilots and rivers. Even as instruments become more complex, the basic principle remains. A cloud close to the ground is both a weather event and an immediate human experience. 7. The quiet network. Barometers, anemometers, vanes, rain gauges, sunshine recorders, and cloud logs together form a quiet network of instruments. Each device measures a different aspect of the same shifting medium: pressure, motion, moisture, light, and form. Over days, their readings may seem unremarkable, small changes, small numbers. Over years and decades, patterns emerge. Trends in pressure, changes in rainfall, shifts in cloud types, alterations in fog frequency. The archive regards these cumulative records as the true memory of the atmosphere. In earlier chapters, we described individual clouds and the engines that move them. Here we have described the weight of the air itself and the instruments that made that weight visible. In future expansions, each of these instruments could be given its own dedicated log, tracing its evolution from simple glass and metal to digital sensors and orbital platforms. For now, the archive closes this chapter with a simple note. Every cloud in the log, every stratus, every cumulus, every nimbostratus, formed under a specific pressure, in a specific slice of the invisible ocean. The barometer, quietly ticking on a wall or recording in a shelter, is the marginalia that tells us how heavy the sky was when each entry was made. The sky is an archive. The archive has traced the atmosphere from its highest, thinnest veils to its darkest, lowest ceilings, treating the sky as a living library of water and light. Each cloud, each droplet, and each instrument reading has been treated as a line in that ongoing record. High above, in the cold, slow air near the top of the troposphere, we met the delicate clouds of the high Étage. Their ice crystals drift in thin cirrus threads and broad cirrostratus veils, marking the paths of jet streams and distant weather systems. These clouds are shaped more by planetary-scale winds and temperature gradients than by anything happening at the surface. In the middle Étage, we followed altostratus and altocumulus layers, clouds that often arrive ahead of large-scale systems. They filter the sun, soften its light, and hint at changes to come. From below, they form a mid-level ceiling, sitting between the cold geometry of the upper air and the noisy complexity of the boundary layer beneath. We then descended into the low Étage, where the atmosphere touches forests, oceans, and cities. Here, stratus, stratocumulus, and nimbostratus clouds form the everyday backdrop of human life. They are the clouds that hide mountaintops, dim city afternoons, and deliver the steady rain and drizzle that quietly replenish the surface. Within this lowest layer, we followed the microscopic story of droplets and nuclei. Sea salt, clay dust, and forest aerosols provided the tiny solid templates on which cloud droplets and ice crystals first formed. Through endless collisions and mergers inside nimbostratus and cumulus clouds, some droplets grew heavy enough to fall, shifting their status from suspension to precipitation. We also met the clouds of vertical development, cumulus and cumulonimbus, that refused to stay in one étage. From small, fair-weather puffs, they can grow into towering structures, sometimes spanning the full depth of the troposphere. In their most developed form, they act as vertical bridges, carrying warm, moist air from the surface to the cold upper layers and returning it as rain, hail, or snow. Alongside the clouds themselves, the archive has cataloged the instruments humans built to measure them. Simple devices like the anemometer, wind vane, and rain gauge turned invisible flows of air and water into numbers and long-term records. More specialized tools, Nephoscopes, sunshine recorders, barometers, ceilometers, and ascending packages, made it possible to track cloud motion, thickness, pressure, and height with increasing precision. Taken together, these observations show that the atmosphere is not a static backdrop, but a global engine and an evolving archive. Heat moves from equator to poles. Moisture cycles from surface to sky and back again. Pressure rises and falls like slow tides in an unseen ocean. Clouds are the visible handwriting of these processes, inscribing short-lived pages that instruments and observers work to preserve. In the end, the archive's purpose is simple: to notice, to name, and to remember. Every cloud type, every droplet's journey, every quiet instrument trace is another line in the story of how the Earth's air moves, cools, condenses, and returns. What we call weather becomes, in this view, the ongoing act of the sky writing its own history, one layer at a time. This concludes Archive Log. The data has been recorded. The observations of the high, middle, and low altitudes are now officially sealed into the record. If you found value in this documentation, I invite you to formally join the archive by subscribing. Your presence here ensures the continued cataloging of our world's most intricate and silent details. If this log has assisted your rest, consider liking the transmission. It serves as a beacon for other night thinkers and seekers of stillness to find their way here. If you are drifting now, let my voice fade into the background of your sleep. If you are still awake, know that the archive is always open, holding these truths in the silence for whenever you require them. New entries are added to the archive weekly. Until our next session, sleep well and remain curious in your dreams. End of transmission.